Hi, my name is Felipe Barbosa.
Hi, I'm Buddhik Lakma.
I'm Shakti Ashwin.
This is a presentation video for the coursework 2 from Digital Signal Processing module at Princeton University.
Our task here is to do a pitch shifter, which we will be explaining in a bit.
This is the board which we will be using for the pitch shifting task. This board here is the DS-PIC Model 33F, which is from Microchip. The board is a fairly simple board. It has an input slot, which is a 3.5 mm jack here, at the top with a speaker as well here. It has a gain adjuster which can adjust the gains of your input. The new thing which you have to note is the jumpers here. This one has two options, one for the mic input, the other one is for the direct line. So based on your task, you'll have to shift the jumpers. For now, let it be at mic. So having said about the input, the output also has two options. One is the PWM option, the other one is the codec option. So based on your choice, you can just choose which one you want. So that's pretty much it. Yeah, it has two buttons for your testing purpose. It has LEDs as well. The board is pretty much, that's all we'll be using.
So this is the program we use. We're using MPLAB to program the pitch shifter. Now, what we do is basically include source files, which holds in bits of code and the functions itself that we're going to use in the whole program. Each of them holds multiple functions. Now the header file here essentially links all the source amongst themselves. Right. So this is the main file here, main C. Initial description of the program. Now this is the initialization, the include of all the header files. You can see all the header files being used, pretty much all here. Now frame size, it dictates the size of the frame that we're going to use for the analog input. It's basically to hold in the time domain frame. This allocates all the variables being used for the output of the buffers and internal processes. Now here initiates and creates the driver handler. Now the handlers are variables which are going to hold the value taken from the buffer. Now the buffer is where you save the inputs and the outputs just before you send or receive. Now that leads on to the main one, the main function. As you can see, we got init filter. That's just to initialize values that describe parameters of the filters. Now in this case, we're just using filter negative frequency here, which should be initialized. Right, this part here basically initialize controlling values of the analog to digital process and the pulse width modulation process. This will control certain features on how it's being produced, like bit size and other parameters. Here it starts essentially starts the function, which basically is going to be used, so allows the ADC to read and the pulse width OCPWM here to write. Now that leads on to our endless loop here. Now these bits of codes are the one that are constantly being run. Here's where it's going to be the call of the functions that are going to do the pitch shift, essentially. Right. So here it picks up the signal from the handler. That's the time domain signal. This is the input. The output comes the FRCT audio in. Now this is a array which holds in the values of the handler coming from the buffer, so basically the input value in time domain Also has the frame size to state how long do you want it, which was previously stated there. Next step is the Fourier transform. Now, what Fourier transform does is converts from the time domain to frequency domain. Now, how you do it's assigned in this transform here. So essentially gets the input taken from the buffer, saves everything into the real part, and assigns all the imaginary as 0. Now, keep in mind that FRC int has both the negative, basically the real part, and the imaginary part. Imaginary part representing the negative values of the frequency, the peaks, the negative values, and the real part indicates the positive peaks. Twiddle factor initiates basically the factor that's going to increase the magnitude of each of the samples or in the indexes on the time frequency domain array. And FFT complex, the whole thing is actually run by this function here, FFT complex, pre-established by Microchip. It's initialized in DSP here, .h. Now, at this point, it says FFT, but is discrete because you're still taking in the negative part of the function. Now that leads on to the filter out negative here. Go back to transform. So what it does essentially is cut from 128 to 64. And remove all the negative components using this function here. Has inputs a complex X, and output comes comp workspace, which is done here. So here it assigns the real part of it and assigns to FRT workspace. That's in the array in between. So this part here does the density spectral basically calculates the maximum index on the frequency domain array, which is going to hold the fundamental frequency. Now this index relates to the position inside that array, which directly relates to the frequency. By a formula, you basically just multiply the sampling rate by the number of samples and this index, and you get the frequency, the actual frequency. Right, so that's the density spectral, the power density spectrum. Right. So finally, it comes into the inverse Fourier transform. Essentially, does the opposite of Fourier transform. So frequency domain turns into a time domain. Now the for loop here just increased the volume. We're increasing by 3, and the while here does pretty much what the ADC here does. This while loop, it essentially says it only allows the handler to receive value if it's not busy. Does the same thing here. And this is the function used to write. Now this is the output, the input, where it's saved here, and frame size, basically saying how much it needs to cycle for.
Hi, as my friend described before, how the code is test work. Then the testing bit, we used the same microchip processor. For that, we used our sort of normal human voice to test it whether this is shifting or not. And furthermore, I will describe how it should be correct in the correct shifting algorithm. Before we start the program, we have set up the board using the micro USB, which is in here. We have to plug this one end onto the microchip, and other end goes to the whatever the computer you're using for your programming purpose. To take the sound out, you're using a microphone, which is this Genius microphone, and take out the process sound out, we're using this Genius speaker for that. before that, before you start in program, you have to make sure you've got all header files and source files in your main MPI lab program, which is this is the source file we're using in our program, and the header file, which is corresponding to the source files, we have should be included in our source file and source tree and the header tree, which is essential to work on the whole program. After we initializing those programs, we want to make sure the program going to build it correctly. For that purpose, we just control +10 and it will process the whole thing and give the output of that. After you make sure the program is built it correctly without no errors, we just need to select the starter kit what we're going to use, which is in our case is number 3. After we selecting that, we want to make sure if you have been using this processor for another program before, you want to make sure that the processor being erased without any data in there. Then after that, we can program the microprocessor. I will show you a demonstration how it's work. Our program does work, which is using our normal human voice. Hello, hello. This is normal what it does in our program. For comparison between, we can see so much distortions on there because of the electronic noise coming out. For that instance, to get rid of that noise, we use the aux cable to get the input from the computer, was playing a song or something. We got the same kind of distortion from there. We'll demonstrate that one to you using the aux cable which we used in here. I will play a song. Before that, I will play the original song for you, this is the new original song. Now I'm gonna play the song with the pitch shifted on our program, which is this one. You can hear so much distortions on there. Comparing to the original one, I will play the original song again. This is original song. If you go for the distortion one, you can't get much good effect of shifting. To compare these two results, we found basically shifted version of the correct song, which will be this one. This should be the correct sound. Looks like if we done the pitch shifting correct manner. So you can see there's no any noise at all we can notice in there. And furthermore, we doing some research on that. We found out the frequency shifting is much more interesting as well. This is the phase shifting. I will explain you how it's works. So basically in pitch shifting, it does is shifting the pitch. Method is altering the pitch of a signal without changing any length or duration. But in the frequency shifting, some material is going through. It describes pitch shifting as frequency shifting, but it's two different methods. In frequency shifting, the spectrum of sound will be shifted. The whole thing is it's gonna make the 3-minute song gonna be 6 minutes long. Unlike the pitch shifting, it's altering the pitch of a signal without changing its length. So that's it basically on the program. So hopefully be able to finish it good underneath under the human voice. You can get a good pretty much better shifting on the frequency pitch shifting, but we got some electronic noise. Rather than that, it worked fine. So until next time, see you.